Welcome to EPG Pathshala. We are discussing module 9, which is the second part of catchment modeling. Now in this, we have in the previous model understood the basics as to why modeling is important. Here what we will try and understand is that how to develop a model and then how to evaluate that model, and at the end of this module we will understand a typical standard very popular model which is used by the FAO. So when we see this, that we have to be able to understand that the model that we develop has to serve the purpose for which we have developed it. So in order that the model is able to serve the purpose for which we have chosen it, we should be able to take our model to the stakeholders as well. The stakeholders must also understand the model, and once we have established the model, we should be able to calibrate and validate it. Now these are the standard procedures. We will find that there are times that we don't follow all the procedures as well. Now as far as the model purpose is concerned, as I have been discussing in the previous module also, the purpose as to why we have developed the model is important. Now is it to allocate water resources? Is it to allocate water between different demands? Or is it just to find out how much rainwater can be harvested within the catchment? Now if we want to find out how much rainwater can be harvested within the catchment, the kind of modeling that we will do will be different from that which we will do when we want to allocate reservoir waters between complex water demands. And of course, we also want to understand whether our model is going to be used for forecasting purposes as well. So what purpose we are going to use our model is extremely important to dwell upon. So now here if we take a look at this typical model, what we see here is that we see that we have the problem identification stage. Now in the problem identification stage, we try and find out what is it that we want to do with the model, and then the second step is the conceptualization stage, and then we have the model that we set up. Now as far as the model setting up is concerned, in this case what we take a look at is that once we have used the conceptual model, what are the variables that we will use and whether those variables are available to us or not, and then of course whether we are able to run the model. Then we want to calibrate and validate the model. After we have done this stage of calibration and validation, we are able to go back to our stakeholders, discuss the model with the stakeholders, and then once again come and make changes in the model whenever it is necessary. So while looking at that conceptual plan, what we understood is that the entire process is an iterative process. It is not as if we take the variables and with that we establish the model and we feel that the model will start running. It is never like that. It is always an iterative step that we have, number of iterative steps that we have to do. And it is important that when we take the mathematical terms, those mathematical terms need not always be very complex. They can have simple sub-models as well. So those sub-models actually feed into the major model, the large model that we have. So what we do here is that we establish a relationship now which can be one dimensional. It can also be 2 or 3 dimensional. For example, in case of groundwater modeling, when we do now, groundwater modeling is not always one dimensional. It can have 2 dimensions or 3 dimensions, but just because we have made the model more complex does not mean that the model will function well. What we have to evaluate is whether we need the model of that complexity or not. So based on that, we look at the performance of the model. So when we look at the performance of the model, there are certain factors which are available to us through which we assess the performance of the model. So for example, in case of the rainfall runoff model, when we see that the results are in the form of the stream flow and this is compared with the observed flows, and we are able to assess how close our model is in simulating the conditions of the catchment. And in this case, as you can see from this RMSE equation, the model performance characteristic is dependent on the observations that we have and the values that are generated by the model. So, it is very clear that if the difference between the observed values of the stream flow and the model simulated values, if it is less, then the RMSE value will be less, and that tells us that our model is able to simulate the characteristics that have been predicted by the observed, or that have been actually revealed by the observed values. So, the root mean square method is a very typical method of determining the model performance. The Nash Satcliff efficiency. Now, as far as the Nash Satcliff efficiency is concerned, now here we know that the difference between the observed values and the model simulated values are measured in terms of 1 minus, as you can see. So, it is 1 minus the values of observed and simulated values. So, here what we understand is that the value of E, the closer it is to 0, the better the model performs. So, once again what we really do is, once we have established the model, we simulate the model conditions, and the simulated values are actually compared with the observed values. This is typically done in case of stream flow. So, stream flow is something which is heavily dependent on this kind of error calculations. Then of course, we have this model validation method that we have seen. Now, in case of the model validation method, what we do is we take the observed values and we try and fit it into the model, but we must understand that in case of observation, the calibration that we are talking about, and then the validation step, it is important that we should be having these model values, as in the observed values, but it is not always possible that we have the observed values. For example, in case of stream flow data, yes, stream flow data is available for a number of years, but for example, if we have something like the water quality that we are modeling, then there is a lot of uncertainty. So, when we do this kind of validation, we must be able to take care of the uncertainty. When we take care of the uncertainty, our model performance improves. We are able to give an idea about the range within which this model is going to work, because unless we provide a range of values in which the model works, it is not something that we are not doing modeling very well. So, but once again, let me assure you here that if it is that we see that our we do not have calibration values available to us or model validation values, it does not mean that the model is not going to work well. The reason being, in case of classic water quality modeling, what we see in case of water quality modeling is, today the water is polluted, the groundwater is polluted, the surface water is polluted. That doesn't mean that 10 years, for the last 10 years it was polluted. So, we do not have the previous water quality data, but that does not take away from the fact that modeling is important, even though we cannot calibrate with previous values. What we can do is, we can calibrate it with the help of similar water quality pollution values of a different river system and try and understand where this pollution or where this water quality compromise is going to lead to. So, another important role of models is in the process of decision making, and when we talk in terms of decision making, we are talking in terms of water allocation, wherein the public might be involved. Especially in case of irrigation water demand, we know that the stakeholders are the farmers who are involved, who are the ones who are directly involved in case of the amount of a certain crop that they may be wanting to grow. So, if they want to grow sugarcane, for example, so they need to know how much would be the water that would be available to them from the reservoirs that would be made available to them, and how much is the actual rainfall that is predicted to happen. So, one such model is the CropWatt model, which is used to understand the evapotranspiration requirement of certain crops, and then we find out what has been the rainfall. So, the difference between the evapotranspiration requirement of the crop on a monthly basis and the and the rainfall available gives us the amount of crop water requirement, and then that is conveyed to the farmers. So that is how the decision making process is made more vibrant by using the modeling process. So there are certain key issues that quantitative models such as CropWatt help in decision making. So before adopting quantitative methods, qualitative thinking is certainly required. For example, when I was mentioning sugarcane, we have to of course debate whether sugarcane really needs to be grown in a certain region. So the quantitative model may not be able to take care of the stakeholders in the catchment in that sense, that the qualitative answer is why sugarcane? Why? Because it is a cash crop, because it is a crop on which the farmers are heavily dependent on for their income, generation of income. So those are things which will not come from the software results, as in the CropWatt results. So it is essentially, as we know, a simplified version of reality. No model can be perfectly representing the complex natural catchment system completely or comprehensively. So for each of the catchments we make certain assumptions. So when we make assumptions, we should be able to understand that there are certain assumptions we have made, and based on that we have got the results that we have. So the models today are quite sophisticated, as we know, and they have very high computational powers because of the readily available softwares that we have, but we must certainly understand what exactly we are doing. So even here we can see that if we want to grow rice, let us say, so we can also grow rice depending on the exact crop water requirement that is there. So even there we should be able to exactly assess the amount of water that is required. So if water logging is not required, as in standing water is not required, then we can do away with that as well. So in conclusion, I would like to say that the models allow a deeper understanding of the dynamics of the natural catchment system and are therefore widely used in integrated water resource management. This allows for the concept of sustainability to be widely practiced, especially in the context of water resource management and natural resource management, because when we defined the catchment, we said that catchment is not just water, but it is water, soil and land use that is important, and the models allow use of resources in a judicious manner so that we can use the resources for a long period of time. That is the aim in any case of modeling. So when we were talking about role of models in decision making process, we have started explaining this with the CropWatt model. The reason why the CropWatt model has been taken up is because it is a very popular model which has been devised by the Food and Agriculture Organization, and it is readily available, though we will continue to discuss this in the next module as well. What I want to discuss here is its role in decision making. Now we do understand that whenever we are looking at water demand, the irrigation water demand or the agriculture water demand happens to be the highest. So when we say that 100 units of water are required, out of that 70 units of water are required for agriculture, while 20 units, let us say, are required for industrial water and 10 units are required for urban water system or the domestic water demand. So when the amount of water that is used in agriculture is so large, we have to understand that decision making becomes very important. So the whole point is how the model will help in an improved decision making. So traditionally what we see is that irrigation is done either through the use of groundwater or through the use of canal water. So if this water supply model has to be continued, it means that X amount of water is supplied and that is why that is used. It does not matter what is the actual evapotranspiration requirement of the crop. So it is the water supply. If I am supplied with X units of water, even if my crop requires X by 2 or 0.75x for that matter for the entire month. Because X is available to me, so I will go for flood irrigation. So that is something which has been leading to overuse of water in many places. So it is worthwhile to look at that 0.75x. The question is how to look at that 0.75x. That can be looked at by using the crop VAT model, wherein the actual evapotranspiration of the crop in a particular month can be studied by using the various sub-models that are available to us. One of the sub-models that is available to us is the climate model. So through the climate model, we can study the evapotranspiration, and with that evapotranspiration and the difference in rainfall, we find out what is the actual water requirement of the crop in that particular month. And then this decision can be conveyed to the stakeholders. The stakeholders is not just the group of farmers in that particular district, but it is also the entire system of the Public Works Department irrigation officials, so that they can take a collective decision as to how much water needs to be released, so that we are able to manage our waters more. Now this decision making is definitely going to help in case we want to grow some other kind of crop as well. So that alternative arrangement of 2 or 3 crops is something that can be taken, because the evapotranspiration rates and the actual crop water requirement will be available to us. And this is the kind, or this is the level of modeling that we need now, so that we are able to actually give a hands-on decision to the people who require it most. Now in this, of course, the communication to the stakeholders also becomes very important. So there is always supposed to be a science and social interface, which many times is missing, and so the decision does not get conveyed. So here, when we are talking about the agroclimatic zone, so we say that depending on the agroclimatic zones, we should be able to give the decision on the crop water requirement. And why the agroclimatic zone is important is because the evapotranspiration requirements of the same crop, for example if we take rice or sugarcane, will vary from place to place, because it depends on the kind of soil, it depends on the kind of temperature that we have, and so the evapotranspiration requirement is not uniform. It depends on the zone in which we are doing. Therefore, the water supply that is provided need not also be uniform. It can also be varied over a period of time, as well as over a period, or a spatial distribution can be there. And if we practice this, then we will be able to address the water scarcity issues. And this is why modeling is becoming more and more popular, and the thrust towards having simpler models which are able to solve our problems, rather than complicated models wherein we take numerous variables into consideration, yet they may not be able to exactly replicate the results that we are looking for, which will actually help us. So if we are able to put a complicated model, but the result that is given to us is not something which is actually replicating the ground situation, then that is something, then the model has not served its purpose, to be honest. So if you want the model to serve its purpose and actually help in decision making, this is how it should be done. Thank you.